So let's talk about Isaac Newton. This is the man who basically wrote the rulebook for how the entire universe moves. We're going to dig into his work and see how he explained everything from a falling apple to the planets in the sky.
You know, it all kicks off with a really simple question. We've all seen something fall, right? But have you ever really, truly stopped to wonder why it falls straight down? I mean, why not sideways or up?
And then you've got the other half of the puzzle. While stuff is falling down here on Earth, the moon is just up there, hanging out. What's stopping it from crashing right into us, or just zipping off into deep space? Now, these seem like totally separate problems, but Newton had a hunch they were connected.
And that right there, that's where Newton's genius really shines. He saw that he wasn't looking at two different mysteries. Nope, he was looking at two pieces of the exact same puzzle, and he knew they were linked by one single revolutionary idea.
So, picture this. The year is 1666. The Great Plague is raging, so Cambridge University is shut down. A young Isaac Newton is basically stuck at home, and this unexpected time off, what people now call his miracle year, gave him the space to just think and watch.
Okay, so let's clear something up. We all know the story about the apple hitting him on the head. It's a fun image, but it probably didn't happen like that. The reality is actually way more interesting. He just saw an apple fall, and it sparked this incredible question in his mind. Could the very same force that's pulling this apple down to the ground be the exact same force that reaches all the way out to the moon and keeps it locked in orbit? Now, to even begin to answer a question that huge, Newton realized he needed some ground rules. He had to figure out how things move in the first place. He needed to create a kind of toolkit for the universe, and that toolkit became his three legendary laws of motion.
Okay, so law number 1 is all about inertia. And honestly, the easiest way to think about it is that objects are kind of lazy. They just want to keep doing whatever they're already doing. If something's sitting still, it'll stay still. If it's moving, it's going to keep moving in a straight line at the same speed forever, unless something else gives it a push or a pull.
And you see this everywhere. A soccer ball isn't going anywhere until you kick it, right? That kick is the outside force. Or think about a satellite coasting through empty space. There's almost nothing to slow it down, so it just keeps on going and going. That's inertia in action.
All right, on to the second law. This one gives us the math, the famous F equals ma. It's like a recipe that connects force, mass, and acceleration. Basically, it tells you exactly how much an object will speed up depending on how hard you push it and how heavy it is. And here's a perfect real-world example. Why is it so ridiculously hard to push a car compared to a bicycle? Simple. The car has way more mass. So according to F equals ma, you need to apply a lot more force to get it to accelerate. And law number 3 reveals this kind of beautiful, simple balance in the universe. It turns out forces always come in pairs. For every single action, there's a reaction that's equal in strength but points in the opposite direction. If you push on a wall, that wall is pushing back on you with the exact same amount of force. And the most epic example of this? A rocket launch. The rocket shoves super hot gas down with incredible force. That's the action. And in return, the gas pushes the rocket up with an equal and opposite force. That's the reaction that lifts the whole thing right into space.
Okay, so now Newton has his toolkit, his laws of motion. He's finally ready to go back and tackle the big one. What is the secret force that connects a falling apple on Earth to the moon way up in the sky?
His answer was a concept he called universal gravitation. And the idea was just breathtaking. He said that every single object in the universe with mass pulls on every other object. That's it. The more mass or stuff an object has, the stronger its pull. And the farther away you get, the weaker that pull becomes.
And this is the big payoff. This is where it all just clicks into place. The exact same gravity that pulls the apple straight down is also pulling on the moon. So why doesn't the moon just crash into us? Well, because it's also moving sideways at a tremendous speed. It's in a constant state of falling towards Earth, but it's moving so fast sideways that it continuously misses. And that state, that perfect balance of falling and missing, that's what an orbit is.
But you know, Newton wasn't a one-trick pony. His mission to figure out the universe's hidden rules didn't just stop at gravity. During that same incredibly productive time, he decided to tackle another everyday mystery. What exactly is light?
His experiment was just so simple and elegant. He blacked out a room, let just one little beam of sunlight sneak in, and put a glass prism in its path.
Now, for centuries, people thought the prism was somehow adding colors to the light. But Newton proved them all wrong. He showed that the prism was just separating the white light into the different colors that were already hiding inside it. White light wasn't pure at all. It was a mashup of every color in the rainbow.
So what do you do when you've basically cracked the code for motion, gravity, and light? Well, you write it all down. You publish the official rulebook for the universe.
And it all came to a head in one single monumental year, a moment that would literally change the course of human history.
He published his masterpiece, a book that's famously known as the Principia. It is without a doubt one of the most important scientific books ever written. It laid out a mathematical vision of the universe that was so powerful it would stand as the final word for more than 200 years.
So what was inside this game-changing book? Well, you had the whole shebang, the 3 laws of motion, the law of universal gravitation, and even proof that planets move in ovals, not perfect circles. But here's the wild part. To describe all this stuff, like a planet constantly changing speed or an apple accelerating as it falls, he had to invent a brand new kind of math to do it. We call that math calculus.
You see, the Principia wasn't just some dusty old book. It was a line in the sand. It kicked off a whole new era of science and gave us the very foundation for the modern world.
So why does any of this matter to you and me today? Because of Newton. Physics stopped being just philosophy and became predictive. We could use his math to calculate the future positions of planets, which is the groundwork for all space exploration. Engineers could finally design bridges and buildings with mathematical certainty. But maybe the biggest thing he gave us was the idea that the universe isn't just random and chaotic. It follows elegant, consistent rules that we can actually figure out.
And that leaves us with one last thought. This entire scientific revolution started with something so ordinary, a falling apple. It really makes you wonder, doesn't it? What simple, everyday thing are we all looking at right now, but not really seeing? What's the next falling apple that's going to completely change how we see the universe?